Welcome back to our 31-week series here on this channel about the Chemistry of Indoor Environments program. This is where we're breaking down the high-level research that was done over 10 years in this program called CIE. Home Chem was a big part of that, and we've got dozens of videos about that experiment that we were introduced to. This is going to be an interesting one. So Tara Kahan is in the show Home Diagnosis, which is our series on PBS. She's great. She's been on our science advisory board, in fact. And so what she's talking about today is cleaning. She was stuck during COVID in her house, like many of us. And so she decided to start experimenting on her own house with her own family. This is what she found out, which is kind of surprising. Here we go.
All right, thank you. I'm very excited to be here in the surface session so I can talk about gas phase measurements. And so, yes, my alternate title is Family Fun. But, all right, so I'm going to give you my conclusion slide first, which a lot of the conclusions that we've drawn from our research are pretty intuitive, right? You can well imagine that ventilation, location, cleaning method are all going to affect exposure and concentrations of emissions from cleaning products to the gas phase. But we're going to dive in a little bit deeper in the work I'm going to talk about, specifically about spatial heterogeneity and how cleaning method can affect concentrations.
Okay, so first, spatial heterogeneity. Homogeneity would mean everything is the same. Heterogeneity means it's different depending on where you're talking about. And this is actually perfect for our channel, like almost everything that these guys are talking about at this conference that we're breaking down in this 31-part series. A home is all about spatial heterogeneity. This particular bedroom might have a problem, and you might not have a problem over in this bedroom that you can sense. And this goes for things that you can't necessarily sense too, which would be like these very fine gas phase measurements that they're talking about, or particles, things that you might not smell because you don't have a sense of smell, which I'm a man. As I get older, I'm going to probably follow most men, and I'm not going to be able to smell much later. My bride will be the one who smells things in our house. So important to listen to the people who can sense these things, but some of this stuff you can't actually sense, or you just won't pay attention to it. So spatial heterogeneity, super important.
All right, so before I start talking about results, I want to talk a little bit about the method that we used for all of the studies I'll be talking about, which is cavity ringdown spectroscopy. And there have been so many really lovely studies by people here, by Delphine Farmer, John Abbott, Brandon Boer, Nick Carslaw, and others, getting really nice measurements of organic and inorganic species released following using bleach or other cleaning agents on floors. We can't do that, but with our cavity ringdown instrument, what we can do is target specific molecules. So in this case, we're using a hydrogen peroxide gas analyzer that with the help of John Abbott and John from the University of Toronto and John Hofnagel from Picaro, we've been able to modify our spectral analysis method so that we can detect and quantify both hydrogen peroxide and hypochlorous acid, HOCl, which is one of the major emissions from bleach use.
Okay, quickly, I thought this was kind of interesting. Cavity ringdown spectroscopy. Spectroscopy means investigation using light. So what this thing is basically, well, I've described how several of the other instruments that these researchers use, like mass spectrometers or gas chromatographs, work. This one is kind of interesting. So what they do is they use a laser, and they essentially use mirrors. So they pulse a laser, and they watch as that pulse of light goes back and forth between these mirrors. Like basically it's shining a laser through space and seeing when it gets interrupted by something. And basically a molecule would need to pass in the way of the light for it to diffract. And at that point, you know what the molecule is by the way that it diffracted the light. I guess is the way. Like, I'm not a chemist, just so that in case this is the first one of these that you're seeing. My specialty is understanding what these guys have been doing for the last 6 years and then trying to explain it to the rest of us. So what they're doing by using these lasers is taking this tiny little package and they're making the laser like miles and miles or hundreds of miles long. And so they're able to then make it really sensitive. They could shine that light and it can go back and forth and back and forth. And if even one molecule goes through that light during the course of that entire, bouncing back and forth, then bam, they got one. Now, it's not about precision, it's more about sensitivity. So they're using this instrument to find really, really small amounts of things, which is this hydrogen peroxide, H2O2, and hypochlorous acid, which is one of the bleach byproducts here. So anyway, I just thought that that was really interesting. They're using colored lights, by the way, to tune for looking for particular species of molecules.
So this method, I think, is a really nice complement to SIMS, to chemical ionization mass spectrometry, because, well, we can't get the speciation and sensitivity of SIMS. We can put this instrument pretty much anywhere, right? And I can tell you that this instrument was running on a dining room table for about 2 months before the spouse who was not involved in the research started complaining. So this is a very non-intrusive method that I think is a really nice complement to the techniques that have been discussed previously. Okay, so first of all, hydrogen peroxide is a common cleaning and disinfection tool, a very common alternative to bleach. And until recently, though, I mean, it sounds so obvious. If you use hydrogen peroxide-based cleaners on surfaces, you're probably going to get hydrogen peroxide in the air. The end. No, so until recently, though, this really wasn't quantified. So, how much hydrogen peroxide is released, and we specifically wanted to know whether we might be making hydroxyl radicals from photochemistry of hydrogen peroxide. Turns out not too much, which was disappointing because that would have been fun. But the emissions themselves, I think, are fairly interesting. So we did 2 different studies. One was in a chamber. So Shan Zhou, who was a postdoc in my group, really led that work. So this is an environmental chamber at Syracuse University. And so we have a linoleum floor and painted drywalls. And then we had a suite of measurements, including our hydrogen peroxide analyzer. The inlet was in the middle of the room. There were fans running, the usual, let's get good air mixing, stuff like that. The second one was led by my, at the time, 4-year-old research assistant. Was performed in a 2-story home. And actually, we had to make our own hydrogen peroxide cleaning solutions because in the early months of the pandemic, the commercial ones were all sold out. So the internet had lots of advice on how to make cleaning solutions, most of which were terrifying, but diluting hydrogen peroxide in water sounded okay. So we did that. And so this was, this first experiment we could say is a very controlled environment, and then this one is a very uncontrolled environment. I did the cleaning experiments, and my grad student, Pedro Souza, who was stuck in Brazil at the time, did the analysis.
Okay, so a couple things here. Hydrogen peroxide. I looked at this on we used a hydrogen peroxide here at the house to clean drains, and it's like a 3% concentration. So there's only 3% hydrogen peroxide in a bottle of hydrogen peroxide solution. The rest of it is water. And I was like, why are we using such small amounts? And Tara goes, well, actually, that is super concentrated because what we're talking about is parts per 100. That's what percent means. So you're looking at out of 100 parts water, 3 parts will be hydrogen peroxide. That's parts per 100. When we're talking about air, normally we talk about parts per million, parts per billion in terms of like ozone, for example. Okay, so then hypochlorous acid, which is a bleach background. Both of these things, hydrogen peroxide and bleach, are used for disinfection. However, we're going to get into later, like people thought that they were just disinfecting with these these solutions, and in fact, they were often not actually doing that. But they're both oxidants. which means they both induce chemistry. That's one of the things that makes them good, at ripping things apart, disinfecting, which is, like, uh, just to be clear, I'm not saying disinfecting is a good thing. And for most people, this is like something that's an extreme case, which COVID was at the very beginning of the pandemic. Both hydrogen peroxide and bleach were sold out where she was. She was saying that she had to make them. Um, don't don't mix chemicals. That was what she was talking about with these Darwin Awards that she was looking at online. These like, oh, how to make cleaning solution to disinfect your home. Super dangerous. Like, for example, everybody knows, I hope, don't mix bleach and ammonia because it will literally make a gas that will literally kill you. And that actually can happen not on a killing you front, but doing really bad things to your body and your brain if you mix any cleaning chemicals, because chemistry is what we're talking about. Chemistry, again, is the making of new chemicals that were not there to begin with.
And so here's an example of some results on a day in June, or yeah, a few days in June in the house. And so what we can see is whenever we clean, we see this spike and then decay of hydrogen peroxide, which is what we've seen time and time again, right? If you read any of the papers about bleach use, pretty much all of the inorganic and organic species that we see, there's a sharp spike and then a decay back to background concentrations. So we see that here. We see a lot of variability in peak concentrations. And I don't have time to talk about it a lot. You can read about it if you want to, but a lot of this variability has to do with what surface was cleaned. Whether we cleaned a stone surface or a wood surface actually made a big difference. The distance of the surface cleaned from the inlet, and whether the 4-year-old opened these back doors in the middle of an experiment, as shown in trial 2 and 6. So we did some inadvertent ventilation studies. But something else that was interesting about these results, other than the fact that at one point we actually got up to 1 part per million hydrogen peroxide, which is really high and scary, but only happened once, is that these decays were quite quick. The decay rate constants that we measured were on the order of 10 per hour to 20 per hour, which was much faster than could be due just to air exchange, because the air change rates were about 1 per hour. So we thought this might be due to surfaces. See, I do talk about surfaces. Yay! So in the chamber study, we were able to look into the effect of surfaces in a very high-tech way. We painted cardboard rectangles, these big slabs, and then we hung them in the chamber, kind of like clothes in a closet, to increase the surface area. And so we had 3 conditions. One was in the empty chambers. That's a very low surface area to volume ratio. And then we had an intermediate surface area and then a high surface area to volume ratio. And what we can see is that looking at the peak hydrogen peroxide levels that we observed, they're highest when we have the lowest surface area to volume ratio, so in the empty chamber, and they are lowest when we have a lot of surface area. Even more telling maybe is that the rate constant for the loss of hydrogen peroxide in the air increases from about 10 to over 30 per hour when we increase that surface area. So it does seem as though surface loss is a very important fate for hydrogen peroxide in these studies. And also what was interesting was it appeared to be irreversible. We never saw the hydrogen peroxide coming back off of those surfaces. But now listening to Vicky's talk earlier, I'm like, okay, maybe it's just that paint is really weird. Maybe it's the titanium dioxide, or maybe it's that it's acting as, I don't know, maybe there's actually diffusion within the paint or drywall or something, but there could be some surface chemistry going on there, which would be really interesting, I think.
Okay. Now, a couple things. Sean Zhou was in the previous slide mopping. She and Tara are both in season 2, episode 12 of Home Diagnosis. It's all about photochemistry. It's all about the sun. Anyway, I highly recommend that you watch that. That's really interesting. And she talks more about other things. But this decay, so what you're seeing here is the amount of hydrogen peroxide in the air is the highest when there's less surfaces. And the thing, I will remind you, about homes is that they have an incredibly high surface to volume ratio. That is the thing that these atmospheric chemists started really freaking out about when they started coming indoors and measuring these indoors as part of this program. This was the beginning of that research on like a grand scale. There, of course, indoor air quality has been researched for a couple decades, but it hasn't happened on this depth. And so what this means is that this stuff is ending up on the surfaces or in the surfaces in the case of drywall. And we'll get more into this in future sessions. So I hope that you stay subscribed for those. But the 10 to 20 per hour decay that you can see coming in here, and up to 30 per hour decay at the bottom graph here, right here, this is way too much to be accounted for by just air leakage. So it's not that it's leaking out. That's how they know that it's ending up on and in the surfaces. And the fact that it doesn't come back out, Tara thinks is maybe chemistry, but also chemistry has to be induced in air with a catalyst of some kind, like photochemistry is the sun inducing chemistry. So if it's on a surface, there has to be something else that's on the surface that then induces that chemistry to happen, because these molecules, like, this is where I get confused too. And again, there's like, this is an ongoing conversation. So hopefully you stay tuned through all 31 sessions. I will be smarter. You will be smarter. But since hydrogen peroxide itself is like, they wouldn't call it a catalyst, but it's an oxidant. I would think that it lands on the surface and then it starts to react with things. And I just have to say, I asked Tara that. She said, well, maybe, but chemistry, like the changing of chemicals, is actually not. When I say on this channel, the air is on fire, literally, she's like, technically, yes, that's true. And it's a very pretty thing to say. It's very exciting. I don't think that that's exactly how I describe it. So she thinks that chemistry is happening a lot less than people like me who are trying to like get people activated about it and motivated to do things about it with ventilation and air tightness, things like that. It's probably happening less often than we're implying. So I just wanted to point that out. Her colleagues, I've asked that of other people, and they there seems to be some disagreement, is all I'll say about that. So I think that some people think that chemistry is happening a lot more often, but she's one of the kind of more caution. She's like a very staid person, even though she's very bubbly. She's like not overexcited about how this stuff is working. So she's clear about something is happening here. She does not know what is happening, and more research is required.
Okay. So bleach, which has been done before. Yes, this is our TOC picture for our paper. Because again, I'm very high tech. But so in the past, people have looked at emissions from mopping floors using aqueous hypochlorous or sodium hypochlorite bleach solutions. We wanted to look at two things. One is one is exposure at different distances from the cleaned surface, and the other was looking at different cleaning techniques. So I think all the studies I'm familiar with, people have mopped floors or sometimes use like disinfectant wipes. We decided to look at disinfection. So we used a commercial bleach spray, and the manufacturer said to disinfect, wet the entire surface, so the interior of the bathtub, till it's fully wetted, and leave it for at least 10 minutes. So that's what we did. The hydrogen peroxide work, I should say, was done in collaboration with Trevor Vandenborre and Cora Young and Jensen Zhang at Syracuse University and Nick Karsla. So very multinational. This work was done as a collaboration between my group and Trevor Vandenborre's group. And it was led by Anastasia Stubbs, who was a PhD student in my group, and by Melody Lau, who was a master's student working with Trevor. So we followed the instructions, and we put the inlet at different distances from the bathtub surface. So I'm showing HOCl levels that we measured when the inlet was about 1.5 meters and about 2.3 meters from the bathtub. So in one place it's in the middle of the room, and the other it's by the door, as far away from the bathtub as we can get. And I mean, these are pretty similar. We're getting about 100, 150 parts per billion, which is similar to what other people have reported during bleach cleaning.
Okay, quickly, 234 centimeters, 8 feet. 165 centimeters, 5 feet. So those two distances, she's saying about the same. She's going to get into a much closer for the person who is actually doing the cleaning or the disinfecting. This is the next thing that happens. And by the way, When she's talking about the manufacturer-directed cleaning method for soaking the surface, this is something like I've been a trainer for 15, 16 years now, and I have to say that reading instructions is something that is a uh, endemic problem with human beings. We're just not good at reading instructions. So normally, people would use this and they would be doing what's called cleaning instead of actually disinfecting. In order to disinfect this bathtub, you must first clean it. You can't just step into this room and then spray this bathtub down, leave it for 10 minutes. Is not following the manufacturer's instructions. You have to clean it first, then you come back over and you're going to disinfect it. And so a lot of people are using these materials and they think they're doing disinfecting, but they're actually cleaning. They're getting all the same chemical and chemistry byproducts, and they're not getting the main thing they wanted when they started using this freaking thing, which is disinfecting of the surfaces. So it's like worst of both worlds at that point.
But if you're the person doing the cleaning, and I always have to act this out, so I'm going to, this one frame, your head is, actually pretty close to the surface there, right? My arms, I don't know, I don't think that's a meter. So you're pretty close to that. So your exposure might be different near the surface than it is further away. So we also looked at a distance of 33 centimeters for the inlet. And we've changed the scale now. But the average HOCl concentration that we saw was 21 parts per million now, which was really high. And even worse was this didn't go away. I showed those with the hydrogen peroxide. You have that increase followed by a decay. When we followed this disinfection method, we saw an increase following cleaning. And then it just stayed steady until here we see in this lilac area is where Anastasia scrubbed and then rinsed everything down the drain. And so for up to 40 minutes, we did this and never saw a decrease in the HOCl levels.
Okay, so what does HOCl and for that matter, H2O2, which is hydrogen peroxide, what do they do to people? And I asked Tara this. They are both oxidants, like we talked about. So they induce what's called oxidative stress, which is a reaction in your lungs. So you're breathing this stuff in, and this goes for all kinds of different things that like ozone does the same thing, causes oxidative stress. So when you're, flying at high altitudes, or when you have an ozone generator, for God's sake, don't do that. Don't buy ozone generators. Don't let any of your friends. It's going to come into your lungs and it's going to start oxidizing on the lining of your lungs. And then your lungs start freaking out and they start having kind of like a similar to an allergic reaction, I suppose. And then your body goes a little bit haywire. So the health effects of hypochlorous acid have not been studied, actually. Chlorine gas has been studied, and chlorine gas, which is just Cl, not HOCl, that uptakes to squalene. Squalene is one of the key components in skin oil. And so your body, we've already talked about this and we'll talk about it more. Your body is a sink for chemicals. So chemicals are landing on our skin, riding around with us, and then coming back off other places like ozone from airplanes, like I just mentioned. You get some on your skin, you take them home with you, and then you off gas them into the air. So that can happen. And also, if they can then do chemistry on your skin, which sounds and probably feels weird, but it's happening to us all the time. And again, we're not sensitive to this stuff. HOCl absorbs a longer wavelength, which is closer to visible light, which means that it can break into OH and Cl. And OH and Cl are both bad. OH is hydroxyl radical, and we've talked about this. I'm linking a video on screen about the hydroxyl radical. We call it the Don Juan of indoor chemistry. And then Cl is chlorine gas, like we just talked about. And chlorine gas is super reactive and also bad for people. So that's kind of where she's at with these two and why this is important that she's been talking about this.
And we think what's happening is that this was kind of a foamy spray. And when you spray it on and leave it, it left this sort of residue. So we think you're just making this constant source of HOCl. So yes, you're losing it through air exchange, maybe surface loss and stuff, but you're just continually producing it. So the cleaning technique can make a big difference. And for people who are doing the cleaning, especially as their job, their exposure could be so much higher than we would expect based on measurements that have been done, right? Like with room average volumes. If you're the one actually doing that cleaning, the exposures might be very high. And so I don't know of any recommendations for HOCl levels, like limits, but Cl2, chlorine gas, is co-emitted. And based on the ratios that people have reported of chlorine gas to HOCl, we expect that chlorine gas concentrations in our experiments were probably about 4 parts per million, which is well above the 15-minute exposure limits that are recommended between 0.4 and 1 part per million. So even though room average values may not be that high, people who are doing this cleaning may be exposed to levels well above what's considered acceptable limits.
So just like, and she's going to get into her thanks in just a second here, but just like our carbon monoxide, if I was going to be going into an unsafe space with combustion happening in it, I would wear my carbon monoxide monitor on my chest, right next to my face. That is not how these standards get written. When it's like, oh, workplace safety for people who are cleaning is, oh, it's supposed to be this much. They're not measuring it right where the cleaning person is going to be next to that cleaning surface. So this is where, again, a lot of these standards, and James Scott talked about this in season 3 of Home Diagnosis, standards are made by largely industry people, not the government, not independent researchers. It's industry is about a third. About a third is consultants that are independent but work for the industry people. So it's really 2/3 industry, and then 1/3 governmental and independent researchers and academics and things like that. So really, like, this is the issue, is we need to look more deeply into all of this stuff as we go.
Okay, so with that, I want to thank a lot of people, and I want to put a special thanks to my little lab assistant, who here I am showing helping me write a manuscript.